Right, we should get started. We had been discussing various sensory and perceptual systems, most especially hearing, and then we spent quite a bit of time on vision, which sort of fair and unfair, it's fair, and that researchers in psychology has spent so much time on vision. And less time on hearing, but still an awful lot of time on hearing. We're going to touch on today two, maybe three-ish other senses. We're going to cram them all into one day, for which I apologize. But in a way, that's also kind of proportional to how much work has been done on them, which isn't to say we don't understand anything about them, just we haven't spent that much time. So a little awkward to put it in this framework, but we'll talk about the skin senses. So it turns out that you are indeed enveloped in skin, and skin is sensitive, wonderfully sensitive to all sorts of things. A very small subset of those things have been actually studied. So we'll talk about mechanical forces or pressure. We'll talk about temperature a little bit, and we'll talk about pain also a tiny little bit. Okay. So we'll talk about skin sense, and then we'll talk about the chemical senses, should time allow, both olfaction and perhaps, if we have enough time, gustation, right, which is, of course, maybe not of course, smell and taste, right, which are closely related to each other, but are studied separately. Right, so that's today's plan, and that will kind of bring to a close all the perceptual stuff. Okay, so let's talk about skin. So your skin is kind of infused with receptors. Your skin is actually the largest organ of the body. We don't usually think about it as an organ. We often don't appreciate it, except maybe when it's dry and itchy. And we also have receptors in the muscles, which are also going to kind of play a part here. We're going to concentrate primarily now on the skin itself and neglect the muscles. But when you move around, it is both your skin and your muscles that give you that sense of moving through space. And so the receptors in the skin and also in the muscles are responding to pressure, pain, and temperature, the three dimensions that we're going to attend to here. Right, so by pressure, we mean some sort of mechanical force. And this little kind of strange diagram is actually indicative of how people study this. Right? So they want very tightly controlled mechanical forces. And so they bring down a little arm here. Right? And that arm may move with just a tiny little bit of force with a particular frequency. Right? So it goes back and forth, like literally comes down, goes back and forth on your skin, just the slightest bit. Okay, so that's pressure. Now, of course, you can also feel pressure from your clothing. You can feel pressure in a lot of different ways, but this is kind of the paradigmatic way to study it. You also, of course, feel pain. This is not how pain is studied. You don't make somebody fall down and get their knee. But people do study pain, particularly as it is experienced through the skin. And then people study temperature. And the study of temperature is relatively small compared to these other areas. So touch for us, in this broad sense, kind of stepping back a little bit, right, away from these three particular dimensions, touch is this kind of many splendored thing, right? And there are people who write beautifully about touch, the importance of touch in a lot of very practical ways, things like posture. but also in, or practically quite right, but kind of without much romance to it, right? I mean, this posture, this standing up, it's very important. It turns out your sense of touch in the broad sense is indeed involved in posture. You can also do things like object identification. Touch. We don't always think about it that way. We tend to think about object identification as a function of vision. But if somebody hands you something and you can't see it, it doesn't take you very long to go, oh, it's a roll of paper towels. Right? So you can do that. It's all through touch. There's, of course, the question of how your visual understanding of something, your visual perception of something relates to your touch perception of something, right? And those two things have been studied quite a bit. When you move through space, your sense of touch is important, both, so perhaps most dramatically if you're walking along, you literally have pressure differences kind of rolling across the bottom of your feet as you're taking a step, but also stretch receptors in your muscles, receptors in your joints, stretch receptors also in your skin are all involved in going, oh yeah, I'm moving now, moving backwards. And so all those things together are somehow coordinated. Then there's stuff which is kind of away from what people who do like the basic level perception aspects of touch are interested in. Things like emotional development. So it turns out to be very important for babies to be touched, particularly early on in life. So in a NICU, right, a neonatal unit, they actually now put the baby right on the mother's chest or the father's chest. Sometimes mom and dad will alternate in and out, right? So, it's my turn to go in and have the baby lie on my chest. And that turns out to be important for emotional development, but actually just development generally and increases survival rates as well. Right? So that's kind of interesting and a little bit hard to explain, right? It's not obvious why that would be the case. And of course, for humans at least, sexual behavior is also wrapped up in touch. So probably connected to the sort of emotional connections that we make through touch. So touch is just very important to people in lots of different ways. And it's kind of hard to study, a little bit neglected probably. So this is a cross section. So that's kind of the stepping back view. Now we're going to zoom in and get to some of the nitty-gritty things that people have found anatomically, and then a little bit of relating them to function. Okay, so this is a cross section of skin. And this is the sort of thing you might find in the doctor's office while you're waiting, right? Every time I go to the doctor's office and I see one of these, I'm like, man, biology. Who thought of this? Hey, this is just amazing. And it's so complex. Even just a little tiny piece of your skin has all this going on. How could this possibly exist in the world? Right? It's just quite remarkable. So here's a little bit of your skin. This is obviously the outside of your skin. This particular patch of your skin has a little bit of hair coming out of it, right, to kind of be representative of some areas of your skin at least. And what you'll see here, and we're not going to do all these, we're going to do a bunch of them though, are various and sundry receptors that are all embedded in these kind of early layers of skin without getting into too terribly much detail. So we have these guys here up close to the surface, which we're calling Meissner's corpuscles, and they respond to pressure and low frequency vibrations. So they are a particular type of mechanoreceptor. We know it's mechanoreceptor because it's vibration and pressure. Okay. So that's one type. We also have these Hessian corpuscles down lower. they tend to respond to transient pressure, like on-off pressures, and high frequency vibrations. So another receptor sort of tuned a little bit differently, right? So think about like rods, cones, right? They're all tuned a little bit differently. Well, similarly here in the skin, we've got our receptors are slightly tuned differently. And here we have Rufian corpuscles. They respond best to stretch and steady pressure. So that's some of them. We also have these guys here called Merkel's discs. They respond to light steady pressure, respond best to light steady pressure. And then we have these guys just hanging around, which are free nerve endings. Okay? So they, unlike the other receptors, aren't encapsulated in something that kind of is determining what sort of mechanical energy best stimulates them. They're just hanging around. They tend to respond best to pain and temperature, but the truth is that because they're not kind of specialized, it's very difficult to know what it is they're going to respond to. And they're kind of a little bit of a wild card, a little bit of a mystery still. Okay, so this is, we're going to leave these guys out. This is just root hair, and this is yet another receptor. But part of what's important here is to note that it's not just a single receptor that's responding to some event. Generally speaking, everything that happens to you in the sense of their boring thing, something impinging on your skin, right, is causing many of these receptors to fire all at once. And so much like how you do color, it's kind of the sum of all the activity which says, oh, that's just light touch, no worries. Or, wow, that's really close to painful touch. Maybe I want to move away from that. So these things are being activated all at once, and they're each providing a little bit of information, and the system is further down the line deciding what all that information together indicates about what's happening. Make sense? It could have been set up, right, where there's one receptor for each thing, right? So I have heavy touch. The heavy touch receptor goes off, heavy touch, right? But it would be rare in human physiology for anything like that to exist. Okay, so a little bit about what's in the skin, and maybe even though this is kind of a gross simplification, it's already kind of surprisingly complex. Okay, so that's anatomy as it relates to a little bit of function. When people first started doing this, though, they didn't really have all this anatomy now, and they certainly didn't know anything about pathways or anything like that. What they did have was a lot of curiosity and the ability to ask questions that was kind of founded in psychophysics. And so they started with kind of a psychophysics approach to these two issues, sensitivity and acuity, which are not quite the same idea. So sensitivity is like that threshold question we asked about light sensitivity. That is, what's the smallest amount of energy, here mechanical energy, that a particular patch of skin can reliably detect, right? It's the absolute threshold question. Okay, so that's, again, we have our mechanical arm, so it's hopefully the same every time. So what's the weakest pressure that can be felt versus acuity, which is kind of like the J&D question, the just noticeable difference question, done spatially. What's the smallest separation between two stimuli that can be felt as two stimuli rather than one? Okay. So now this thing has 2 points on it, and it has the ability to separate those further and further in space. And eventually the participant goes, oh, no, that's two things, not just one. Right, and then you put them back closer and they go, no, it's one again. And of course, being clever, you'd be alternating that with really it being one and really it being, you get the idea, so that you can't just guess correctly at the situation. Okay, so you can have this experience for yourself. It's not hard, right? So you take two fingers, right, and you start to slowly separate them, even on your forearm. Initially, small separations, you'll feel like it's one, and then eventually very clearly becomes two. If you want to play around with it even more, you'll notice that on your palm, that separation happens much more quickly. Experience of the separation happens much more quickly at much smaller distances, but on your back, it's like hilariously bad. So you might need a friend to try it at home, but it's like, it could be like that far apart, right? And it'd be like, well, what are you talking about? It's one. No, it feels just like one. And so as it turns out, both your sensitivity and your acuity depend on skin location. And this has to do with a number of different things, but partly the density of the receptors actually in the skin, but also how much cortex is devoted to those areas, right? And those two things are also related to each other. So this is one of the, I can't tell whether I love or hate this graph. It's sort of I inherited this graph, and it's kind of strange. I think it would, so hopefully, I don't know, hopefully it makes sense. So what this is saying, so this is the person's body, in theory, laid out this way. And so rather than just write face, they actually put the bars on the person's face. Too much for me. Anyway, so here we have acuity in the stripy bars and sensitivity in other bars. So we have amazing acuity on the face, and the sensitivity is pretty good too. Right? But not actually the highest that we have, but pretty good. Right? So you can tell things apart really, really well on your face. Really tight acuity. And again, pretty good sensitivity. Right? You in a way, you already know this, because you can feel like even just a single, like if you have a hair on your face, single hair on the face. Like the hair weighs hardly anything, right? And yet your skin is capable of detecting. So you already kind of know this from your everyday experience. So this is really good here. This is on the person's chest. Sensitivity and acuity go way, way down. And so your chest is not particularly sensitive. Your forearm has better sensitivity than it has acuity. Why that is? We could make up a reason. We could talk about evolution or something and make up a reason. And then that reverses again out here on the hand, where acuity is awesome. Sensitivity is good, but not quite as good as on the forearm, which is kind of interesting. And then down here on your leg, you can just forget about it. There's really nothing going on down there. You can hardly feel anything, for better or worse. So that's not that you can hardly feel anything, but compared to like your hand or your tongue is also like super sensitive, actually more sensitive than anything we're looking at here. So you get the idea generally, and you could of course map the back, and the whole body's been mapped and so on and so forth. Okay, so that's what they've done with sensitivity. And it's certainly not very romantic. Doesn't have anything to do with sexual behavior, disappointingly. But that's what they did. Let's talk about temperature. Temperature is weird, right? You have the experience, the impression that you can detect temperature with your hands or with other parts of your skin, right? You know when it's cold. You know when you grab something and it's hot. All that's true. And so you have this experience as if you were directly perceiving the temperature of something. turns out it's you're perceiving something that's correlated with temperature, but not quite temperature as we usually think about it in the physical sense. So mostly what your temperature perception is being run by is the difference between your skin and the object, which makes sense. Right? So if your skin is at one temperature and the object is at another temperature, you put those two things together, that difference that's driving the temperature perception, which again, perfectly sensible thing. But it's a little bit more complicated than that. It's what you're perceiving corresponds to a particular physical dimension called thermal conductivity, and it's the rate at which the surface draws heat away from the skin, or inversely, right? So if you have a flow of heat away from the skin, things feel cool. So why did I make that more complicated? Well, the reason it's more complicated is because you can have different thermal conductivities at the same temperature based on the object's properties. So for example, metal will always feel cooler than plastic because metal has a higher thermal conductivity than plastic does, even when they're at the same temperature. So the plastic will always feel warmer. You can do this for yourself if you're sitting here in the front row. You can reach up and grab this lovely piece of metal here. Actually, it feels kind of warm, so this is not a good demonstration. Never mind. I don't know why it feels warm. Does it feel warm? I don't know why it is. Maybe just kind of the heating system or something. I don't know. This should have felt cool. Not working. It's not working today. So anyway, the theory is this is going to work. So metal should feel cooler because it has a higher thermal conductivity than the table or piece of plastic or something else, right? And that's why when you feel some things, right, it's like, oh, ooh, this is nice and cool, right? Piece of metal, put it up. That's good. Right. And that's why the dog lies down on the stone floor, right? Because it has higher thermal conductivity. And in a way, there's nothing false about that. It actually is pulling heat away more quickly. Right? So that, but it's not at a different temperature. Okay, so the perception of temperature is actually your body moving heat from it to the outside body. That makes sense? To the outside object. Questions on that? Yes, go ahead. Sorry.
Same kind of thing with evaporation, or is that something different?
Oh, yeah, that's a great question, right? So is that the same thing with evaporation? And is that why evaporation feels cool? I think yes. Yes, it is, yeah, because what's happening is the same sort of process. When you have a little bit of wetness on your skin, the evaporation is actually cooling your skin more rapidly, and so the air essentially has more conductivity. That makes sense. So the transfer of heat off of your skin is actually more rapid when it's wet. Unless it's really humid, then you're just miserable. Okay, so that's roughly the story with temperature. Again, this is kind of a psychophysics example, and we talked a little. It's the free nerve endings which are supposedly doing this work mostly, but honestly, it's not particularly well understood. Okay, I'm sorry. Last fly up before. All right, so let's talk about pain. This is not pain in its most general sense. Okay, so I feel in most ways, and I hope you never do, but you can, right? So you could feel pain, in your gut, which is awful. You can feel pain in lots of other places that are not this. This is just pain vis-a-vis the skin, which is also pretty visible. So pain obviously has a lot of functions, and people who study pain always start off their work saying, I study pain. It sounds a little boring, but really it has a lot of functionality. Generally, the function is don't do things that cause damage to your skin. Okay? That is a good idea. So don't stay out in the sun too long. Don't cut yourself. Don't go banging into things. Don't, right? So there are lots of things that you shouldn't do. But generally, your skin is a pretty good indicator of when things are getting too rough. And so that's one of the major functions of pain. Pain is not always functional, alas. You can have pain that is totally non-functional. And that's really a bummer when you have that, right? And it can be kind of chronic. And that can happen even just at the skin. So the pain receptors, which are these free nerve endings, are sometimes called nociceptors. And that's what we will call them, nociceptors. So these are the free nerve endings, all the way back to that initial sort of anatomical slide. So the nociceptors are, again, free nerve endings. There are two types for our purposes. There are the A delta fibers, and these are being classified by their axons, right? Because remember, there isn't a structure surrounding them. There's free nerve endings sitting out there in your skin. And the C fibers, and there are subtypes of these things. It's pretty well understood. But at any rate, so the A delta fibers, the C fibers are a little bit different in what they do, how they function. The A delta fibers are the perception of pain that is most rapid and immediate. Okay? And that is partly because those fibers are heavily myelinated. The C fibers are slower reacting, and that's because their axons are largely unmyelinated. And so you have these two timescales of pain. As if one timescale of pain wouldn't be enough, there are two timescales of pain. So if you stub your toe, maybe you had this feeling, right? You stub your toe, immediately, oh, that's not too bad. And then you go, oh, that really, never mind, that really hurts. And then the C fibers kick in, and you get not just that first feeling of intense pain, now you get this kind of long feeling of pain. There's like that second wave of pain. That's from the C fibers now having their say as well. Yeah, and the A fibers said, yeah, that was bad. The C fibers said, yeah, we think so too. That second, we think so too, is that longer or dull, more throbbing pain. So this gives us sensitivity to tissue damage, that is by mechanical means, but also tissue damage by excessive temperature and other things. So they have all sorts of categories of the nociceptors, again, that are responding to different types of damage. It's not perfectly understood, but well understood to some extent, the anatomy at least. Well, the complicating factor is that all this matters. All this is affected by, I should say, a whole host of psychological factors. Right? So what you believe to be your current situation, your current emotional state, your expectations about whether you were going to get hurt or not. So you can be ready for something and really think it's going to hurt, right? And it's not just that your reaction is higher, like your actual experience of pain seems to change depending on these things. Right? So for a long time, people were like, "Oh, that's just you're overreacting," right? So you're all jazzed up about the shot. You really hate shots, and you're thinking about the thing penetrating your skin, and it's really freaking you out. And then you get the shot. It hurts so much. Well, it turns out that in ramping yourself up, you set your system up so that it actually does hurt more. Like you actually have that experience more. It's very interesting. It's not clearly understood, but you can like show those activations other places in the down the line essentially. So obviously, anxiety increases such things, generally speaking, right? And fear, stress, uh, concentration, so on and so forth, can decrease them. Right? So if you are jazzed up in a particular way, right, where you are in a like fight or flight mode, immediate pain, you're not really too concerned. Right? If you really are like ready to go, either in intense fear or intense rage or something, later on you may realize that you have cut yourself or you have banged your knee very badly or something. But in the moment, that pain will not get through. All right, that's going to wrap up the skin senses for us. Questions on any of that before we go on? So much more we could say about this, but we will move on to olfaction. Olfaction is your sense of smell, of course. So we have a pretty good sense of smell. Nothing like other creatures. Dogs, very famous. We have an incredible sense of smell. Smell is weird. It's about things here, but it's also about things that were here but aren't here anymore. You walk the dog, you'll notice that they are interested not only in the present, but they're also interested in the past. Right? So, oh, what was here a few minutes ago? Wow, this is great. Yeah, there's something really interesting here. Right? So they have this kind of connection that we really don't have, right? I mean, it's rare that you're like walking along and go, it's raccoon here for a while. Skunk maybe, but it's really limited to a very, very small set of things. But they have a tremendous sense of what was in the recent past, and of course what's at a distance now as well. So olfaction gives that to us, and again, it's kind of strange. We've been consistently describing kind of the physics of things first, weekly at least, and then a little bit about the perception. So the physical thing that you are responding to when you have a sense of experience of smell are called olfactants. So these are molecules that are hanging around in the air and that are coming off of other objects. So it's kind of nasty to think about, particular things you might smell, but it's literally tiny little pieces of the thing you're smelling. Sorry about that, but it is. Right, and that stuff has made its way, it's about to get worse, up your nose. So the olfactants, I mean, we could do this as perfume and then it's not so bad. I'll leave the rest of it to your imagination. But the olfactants are things that have made their way into the atmosphere and are now hanging around. It is those molecules that have made it into your nostrils. Okay, so that's olfactant. A type of olfactant that works very well for some critters, not so well for humans, are famous, I'll mention these so are pheromones. So pheromones are used by some species for communication, particularly things about mating, but also signaling danger and territory. Right. So the reason that cats pee everywhere is to mark their territory, and that is a way of communicating to other cats. Fortunately for humans, if that happens to be an olfactant, you can get up your nose. Right. So those things are well established. Again, in humans, maybe. Very famously and powerfully communicate sexual readiness in other species, not so much in humans. There is some evidence, people really like this idea a lot. There's some evidence for, in humans, for pheromonal expression of emotional state. Some maybe, kind of a standard gender identification, olfaction in humans, and that's why this kind of persists, this pheromone idea. people who are in the perfume industry very much like this idea. But to the best of my knowledge, there's nothing on the market that actually, wearing something body wash does not actually work in that way, although it may make you smell nice or not, as the case may be. Okay, so that was an awful lot on pheromones, and they're not particularly important to us as humans, but they do work very well for other species. Okay, so we talked about olfactants. So when olfactants arrive into your nose, your nasal cavity, they encounter this thing called the olfactory epithelium, which is a mucous membrane that kind of resides at the top of your nasal cavity. So here is nasal cavity, and here is this enlarged area here, at least, is the olfactory epithelium. Okay, so it has these olfactory receptor cells, and it has olfactory mucus. And so what happens is the olfactants bind into the mucus. This is not the, like, but don't worry, like when you blow your nose, you're not blowing out your olfactory epithelium mucus. I don't want anybody to worry. So it binds into this mucus. The mucus then it then binds onto the cilia of these olfactory receptor cells. So these are like little cilia, they're hair-like projections. That greatly increases the surface area of these axons, essentially, so that they have lots and lots and lots of binding sites possible within the mucus. But it has to actually go into like liquid to do the binding, which is kind of amazing that it all happened. So from there we go up into the olfactory bulb, and then eventually out the olfactory tract and down the line, which we'll get to in a moment. Right, but that's the basic process. Right, that's the transduction process, if you will. All right, so these molecules become trapped in the mucus, and then they make contact with the receptor cell cilia. So there are 1,000 different types of receptors in your nose. 1,000 different types. Amazing. How can there be 1,000 of them? But they're not one-to-one with odor perception, as it turns out. You can actually get 10,000 different odors out of those 1,000 different types of receptors. So again, it's going to be one of these situations where there are multiple receptors firing for almost every possible molecule that you're able to detect as an odor. Okay. Now, most odors, of course, aren't just one molecule type. Like, yes, you can do that. You can isolate a particular molecule and see if you have reactions to it. But in the real world, the general case is what you're smelling is really complex. Right? It's like you need an analytic chemist to pull all that apart. Right? But you have an experience of it in its, beautiful, complicated form. Okay. So it's not like there's a one-to-one mapping, and it's also not like each thing that you actually smell regularly is just one item, one type of molecule. Okay, so there's not one-to-one specificity between receptor type and odors, right? But there's really, really, really good sensitivity. So you are very sensitive to various odors. Now, not equally sensitive to all odors. It turns out some things you're very insensitive to, and other things you're highly sensitive to. So oddly, things like the smell of menthol, right? That sort of minty smell. I would have thought you'd be really sensitive to it. It's one of the least sensitive things, a molecule that you're least sensitive to of all the molecules, right? So which is kind of surprising. So I have to make just a little detour into the what we call the smell pathway. We go from receptors to olfactory bulb directly to what we call primary olfactory cortex. Usually, in other sensory systems, everybody stops at the thalamus. In this system, we don't stop at the thalamus. Very surprised. People make a big deal out of it, say it's something that sort of makes smell primary in a way. You can imagine the evolutionary arguments they try to make out of that. It's not that it never gets to the thalamus. Actually, the primary olfactory cortex projects to the thalamus itself. But going first to the cortex is something that people make a lot of hay at. Right, so you can see that here. So this olfactory bulb is very close to the kind of the top of your nose there. And there's the olfactory tract, which is essentially a whole set of axons, which are then projecting. Right? And eventually, that all is going to end up here in primary olfactory cortex. It then also goes on to the amygdala, hypothalamus, and various other places. It's not wildly clear what each one of those steps do, to be honest with you, right? So they sort of, it's easy to say where it goes because you're like following the axons. You're like, oh, look, it's going over there. But to know what it does at each location is incredibly difficult. Almost so far has been impossible. Okay, so that's the general pathway. There is a lot of interest in smell as it relates to emotion and memory. You've probably had the experience where you walk into something, maybe a restaurant or a bakery. Oh, it smells like my grandmother's sweetbread, right? And people have this, the emotions come flooding back and you're crying because of the sweetbread, right? So this is a common experience. It turns out to be very difficult to physical life. So it's the empirical evidence for smell having superpowers in terms of memory and emotion, pretty small. But anecdotal evidence, on the other hand, is like overwhelming. Everybody's had the experience. Like literally put back in place by smell. And why that happens, why that feels like that, it's just not clear. And again, one of those things people try to get in the lab, but you can just see how hard it is, right? Like, okay, now I gotta find for you what the smells are, right? What are your memorial smells? Pretty difficult. All right, we are gonna make it to taste. We'll be done. So with apologies to your olfactory systems for giving it such short shrift, we're going to move on to taste. Taste, like smell, is completely a chemical sense, and taste and smell are kind of often related to your real experience when you're like, if you are in an eating situation, it's both the taste and the smell that are contributing. So taste has a number of kind of basic categories. For the longest time, since the 50s, we've identified these four: bitter, salty, sweet, and sour. Reasonable set. And the people thought that everything you taste is some combination. It's like those are the dimensions and like the taste space. And everything else, every taste is in there somehow. So you're gonna need, there's some combination of those four. More recently, it's been proposed that there are perhaps two others. One is called umami, and the other is for fattiness. So umami is kind of strongly associated with monosodium glutamate, which is MSG. So it's used as a food flavor enhancer. Umami translates as yummy, I think, in Japanese, and that's it. It's a Japanese word. And so I'm not sure that's particularly helpful as a description. But things like Parmesan cheese are high in umami dimension, umami property, right? And as an experience, right? So there's something about them you're like, ooh, that's really, really good. So you've probably had this experience, probably you've had this MSG experience, monosodium glutamate, where for some reason you can't stop eating the stuff. Right. So like pretty sure the fries over at what's the place? Ooh yeah. I'm pretty sure they had MSG because I barely even have to use my hands. I mean, right? They're just, you know the feeling? You're just like, oh my God, this is incredible. Oh, these are just French fries. Why am I doing this? It's probably because they have the stuff in them. Now I don't know that. Maybe some of you work there. Maybe you have like a secrecy agreement with them. I don't know. Anyway, but fatty also is now proposed. That is, they're supposed to have the ability to sense the degree to which something is fat now, which makes a lot of sense, right? Because your body really likes fat. Fat is kind of gross, but it's also really tasty. So we believe that we have receptors that are maximally sensitive to each one of these types of taste or dimensions of taste, if you will. So the receptors are primarily on the sides of your tongue, but also kind of throughout your mouth and the upper part of your throat. And of course, they're not evenly distributed everywhere. And you can imagine it's going to get a little bit complicated. The receptors themselves are generally located on these papilla, where the taste buds are in the sides of the papilla. So this would be like a picture of your tongue, okay? And it has these little tiny rough spots. So this is only 50 times magnification. So they're pretty big. They're not gigantic, but they're pretty big. And so here are the taste buds, right? So they're kind of down in these little crevices here. Okay? And these guys have their own, have more structure. Again, biology, whoever made this. So these are your taste receptors in here. And very much like smell, you're binding the molecules, and these cilia are being activated by that binding. They're changing the potential of those membranes. So the taste receptors turn over really, really rapidly. I think it's every 60 days they're turning over. Yeah, maybe they're 10 days. One of them is 10 and the other is 60. Either smell or taste is 60 and the other one is 10. But they turn over all the time. So they're very difficult to study because by the time you got the person back in the lab, they've lost that taste receptor that you were studying, and now there's another one there. All right, and finally, let me tell you about the taste pathways. So the taste receptors then go up to the medulla and the pons, which is interesting because that's part of the regulatory system, right? And eating is one of those things that needs to be regulated and is involved in your own energy regulation. And from there, goes off in two separate pathways. One goes to the thalamus, and then eventually to primary gustatory cortex, but also, and kind of independently, to the limbic system, which is mostly concerned with emotion and memory, right? So this is thought to be like the pathway that allows for identification of what it is you're eating. Like, oats, very nice, right? Or sugar, even better. Jam. And this is like, have you ever had this experience where you eat something that's not edible, like really not edible, like dangerously not edible, and before you even know it, it's out of your mouth, right? Your mouth is like, nope, not that. that's from this kind of action where you get a deep emotional response that is like, no, not coming in here. So this, as well as the sort of nausea you can get, from things which taste really bad and smell really bad. All right, thank you very much. Have a great weekend.
Thank you.